we're going to talk about the method called variation of parameters, which will help us find a particular solution to a general second-order linear non-homogeneous differential equation. And here this is just a general second-order linear differential equation. These don't have to be constant coefficients. They can be arbitrary functions of t. It's going to be important to put it into this form. In other words, if you have something in the form of p of t y double prime plus q of t y prime plus r of t y equals g of t, then just divide through by that capital P of t to get it into this form, like this, where little p will be q of t over p of t, little q of t will be r of t over p of t, and the little g of t will be capital G of t over p of t. In other words, if you start in this form, be sure to put it into this form where the coefficient on y double prime is 1. Now, the first thing we're always going to do is find the general solution to the corresponding homogeneous equation. Now, this assumes you can do that. We've certainly learned how to do that in the case of constant coefficient equations. I should say, when I say this is the general solution, it's going to be important that y1 and y2 be a fundamental set of solutions. In other words, the Wronskian of y1 and y2 should definitely be non-zero. That'll actually come up later and be an important thing. So, assuming we have this fundamental set of solutions, our general solution to the homogeneous looks like this, and now we'll begin our quest to find a particular solution to the non-homogeneous equation. We'll look for a particular solution, y of t, of the following form. We'll write it as u1 of t, y1 of t, plus u2 of t, y2 of t. In other words, the goal is to find u1 and u2 to make this work. Now you should notice that if u1 and u2 are constants, then the function y will be a solution to the homogeneous equation, and that won't work, assuming g of t is a non-zero function. Another thing to notice is that I only care about finding u1 and u2 each up to an additive constant, because if I replace u1 by u1 plus some constant c, in other words, let y of t be u1 plus c times y1 plus u2 y2, that's just the same as u1 y1 plus u2 y2 plus c y1. If I had a particular solution to the equation before, then I'll still have a particular solution because this is the same as the other solution I had, and this is a solution to the homogeneous equation. And the same is true if I add a constant to u2. So since I'm looking for just a single particular solution, to which I will add the general solution to the homogeneous later, and when I look for u1 and u2, I don't have to worry about adding a constant to either one of them. Here's the way we're going to find how to choose u1 and u2, how to choose these functions here to make the function y a solution to the differential equation that we desire. The first thing we do is we're going to start computing derivatives of y in order to plug it into the differential equation to see how to force u1 and u2 to make things work. So we compute y prime using the product rule. We get u1 prime y1 plus uy1 prime. Then using the product rule over here, u2 prime y2 plus u2 y2 prime. Now this already has 4 terms. When I went to compute y double prime, we would have 8 terms. It would get really messy and something very difficult to work with. It's not just that it's messy, it would be something we couldn't deal with much. So we're going to make the following simplifying assumption, and it's going to be really neat how this works out, that if we make the assumption that the sum of these two terms, this term plus this term is 0. Then y prime will just be the other two terms. It'll be much simpler. Now, I can't just make that assumption and hope it's true for the u1 and u2 that I find. When I say I'm going to make this assumption, I will later force this to be true. So that this assumption will end up being justified. So it's a simplifying assumption which we'll later force to work, and then y prime is this simple thing, and y double prime, then we again have to use the product rule twice. That becomes u1 prime y1 prime plus u1 y1 double prime, plus the same thing for u2 y2, u2 prime y2 prime plus u2 prime y2 double prime. Okay, now that we've computed y double prime, and we have y prime, and we have y up here, we plug those into our differential equation, y double prime plus p of t y prime plus q of t y equals g of t, and we ask how can we choose the u1 and u2 to make things work. Well, here's what we get when we plug them in. Y double prime plus p of t y prime plus q of t y is this. This is y double prime plus p of t. I've left off the t's here, so that p is p of t. This is y prime. And of course, this part here, we have q times this is y. And this is q as a function of t, and g as a function of t over there. Now, I claim that all simplifies to this one beautiful little thing. How does this simplify so much? Well, let me circle a few terms here. When I look at u1 y1 double prime plus p times u1 y1 prime plus q times u1 y1, what happens when I add those three terms together? I get exactly u1 times y1 double prime plus p y1 prime plus qy. And since that should be y1, since y1 is a solution to the homogeneous equation, that's how it was chosen, this will be 0. So the sum of those three terms is 0. This all since. And the same thing is true of y2. So not that term, sorry. I'm going to put a box around this term. Here, u2 y2 double prime plus p u2 y2 prime plus q u2 y2, the sum of those three box terms is likewise 0. And the only thing I have left is this term, and this term must equal g. That's this equation here, u1 prime y1 prime plus u2 prime y2 prime must equal g. So I just have to choose u1 and u2 that make this equation true. But remember, I had previously assumed this, that u1 prime y1 plus u2 prime y2 is 0. So I need this to be true, and I need that assumption that I made previously still to be true, so I need these two equations to be true. Well, I'm going to think of this as two linear equations. Remember, y1 and y2 are given. Those are known, and the 0 here, obviously, and the g, those are given. You can think of this as two linear equations in the two unknowns, but now the unknowns are u1 prime and u2 prime. And we can just use linear algebra to solve for u1 prime and u2 prime. You can use even, for solving two linear equations and two unknowns, you can even use something like Cramer's rule, which one doesn't use much in linear algebra, but it gives us a simple way to get the formula. u1 prime, if you remember Cramer's rule from Math 206, u1 prime, our first variable, will be the determinant of, we use 0g here, and then we would have y2 prime over the determinant of our coefficients here, y1 prime, y2 prime. And that's exactly this. The numerator here is minus, the minus is out here, y2 times g, and the denominator is y1, y2 prime minus y1 prime, y2. That's this denominator. And notice that this denominator is exactly what we've been calling the Wronskian of y1 and y2. Remember, y1 and y2 were a fundamental set of solutions to the homogeneous differential equation, so the Wronskian can't be 0, and that's good because that's exactly the condition for the existence of solutions here, and certainly we need that to be non-zero for this to make any sense at all. So this all works because we have a fundamental set of solutions, y1 and y2, to the homogeneous. How do we get u2? Well, again, Kramer's rule tells us u2 prime would be the determinant of y1 prime. Then we would have 0 and g here over the same denominator, y1 prime, y2 prime. Y2 prime down there. And again, this denominator is exactly the Wronskian, and the numerator is just y1 times g. There's no minus sign this time. This determinant is y1 times g. So this tells us what u1 prime and u2 prime are. Of course, in order to finish our solution for the variation of parameters method, we need to know what u1 and u2 are, not just what their derivatives are, but that's easy. We just integrate. So to find u1, we integrate that formula we just had. I pulled the minus sign out, but we just integrate, take minus 1 times the integral of y2g over the Wronskian. Remember, we can always write this as the Wronskian in the denominators, and u2 would be the integral there. Then to finish up, we put those back together and get a particular solution. I'll call that capital Y, which is u1 times our original y1, that solution to the homogeneous system, plus u2 times our second solution to the homogeneous equation, I should say. Notice when we're evaluating these integrals, the integrals come with the integrals come with an arbitrary constant associated with them. We don't need to worry about writing plus c here. We can just pick any value of the arbitrary constant we want. In other words, pick the constant that's associated with these integrals and use any choice for u1 and u2. Again, the reason we can do that is if you use a different choice and add a constant to either u1 or u2 or both, you'll just get a different particular solution because all you'll get is the same solution, capital Y, plus a solution to the homogeneous equation, which would be a different particular solution to the non-homogeneous equation.